Alright, this video is talking briefly about uncertainty, range of uncertainty, absolute and percent error, and just a bit about accuracy and precision. We'll use our lab activity example, finding the height of the balcony in D building. We're going to talk about uncertainty first, and what I always want to ask in my labs is which measurement contributed most to error in total in finding my whatever I was looking for in my experiment. And so in this example of finding the height of the balcony in D building, I had two measurements I took. This is an example now. The distance D on the floor and the angle theta using the inclinometer on a phone. So I ended up saying, for the sake of this example, that theta had the greatest amount of uncertainty involved. And you have to make that decision based on the measurement tool you're using and how you're using it when you're doing your lab. So it's important to make little notes as you're going. Maybe you have this planned out, but you haven't actually done it or completed the procedure. But you notice, this particular measurement I'm doing seems to be, this is probably, you got a decent amount of error here, and try to mark something down quantitatively, like it's probably only accurate within 2 degrees of whatever I'm calling my measurement. So for instance, 45 degrees plus or minus 2 degrees gives me a range. It could be as high as 47 degrees or as low as 43 degrees when I'm a particular distance D away from the balcony on the floor. So when I solve for h, for instance, and using the tangent function here to relate the opposite side, the height, to the adjacent side, the distance to the balcony, I can substitute my values in of 47 degrees as a maximum angle and 43 degrees as a minimum angle to get a range of height. So I have my 5 meters is what I got when I calculated it with 45 degrees, plus or minus maybe 0.5 meters, depending on which angle I use. It's just an example of how I could illustrate that range. We'll do it with some actual numbers here next, so let's see that. We're going to have uncertainty based on my measurement tools and how I'm using them. And so in this case, if I measure the angle of 45 degrees, the tangent of 45 degrees is 1. That indicates I'm looking at an isosceles triangle and that both sides that subtend the hypotenuse are equal to one another. So if I walked backwards until my angle was 45 degrees, I would know that my distance D on the floor, assuming that angle met the adjacent side on the floor, would be equal to my height. And let's say I have that range of uncertainty like I mentioned before in the previous slide of plus or minus 2 degrees. Then I can show my calculations here with 5.0 meters times the tangent of 47 degrees, the maximum angle it could be given my range of uncertainty. I get a height of 5.36 meters, and if I use the minimum angle based on my uncertainty range of 43 degrees, I get 4.66 meters. I can split that difference, or I'm just going to say something that is inclusive of it all. It's 5 meters plus or minus 0.36 meters. Okay, so if those were my actual measurements, that would include, I think what we actually found was the accepted direct measurement of the height. Okay, so when we look at our actual measurement, and notice on the bottom right there I can express my uncertainty as a percentage as well if I want. When I compare this to my actual measurement, I want to, or the accepted value, I want to ask, is our range of uncertainty legitimate? Okay, it should be an honest range that we pick out based on what we identify as contributing to error the most in our calculations. And we want to have as small a range of uncertainty as possible. If we do our labs really well and we take care with our measurements, we should be able to get decent ranges of uncertainty. And I also want to ask, does my actual value or accepted value or standard value fall into this range? And that's how we're going to, one way we can look at and one way we will look at error. Okay, if it falls into our range, good for us. If not, we want to investigate why. We also want to be able to talk about error. Now, plenty of this you've seen before. We want to be able to say what our absolute error, so the difference between, say, what our standard or actual amount is. So say that the balcony is exactly 5.30 meters tall, and my indirect measurement, which I calculated based on other measurements I here call h sub c, say that was 5 meters. My difference there of 0.3 meters is my absolute error. That's just the difference between the two. and I want to be able to calculate my percent error any and all times when it's relevant during a lab. So that's defined as the absolute value of the difference between our accepted value and our value from our lab work. And in this case, that's going to be 0.30 meters, divided by the standard or accepted value. So say 5.30 meters was the height. So I have 0.3 divided by 5.3, and multiply that by 100 to get a percentage. And you see that is a value down there in the bottom right hand boxed. I want to be able to say what my percent error is if we have a standard or accepted value in our lab work. Accuracy and precision, we will just say a tiny bit about this. Accuracy, mostly we can consider it how close to the actual or standard amount our number is. So if we said the actual height of the balcony is 5.3 meters, and the number I got from my lab work was 5.29 meters, we would say, wow, that's accurate. That's more accurate than 5.0 meters. Okay, it's further from the actual amount. This is sometimes referred to generally as trueness in experimentation, and a low percent error would suggest a higher accuracy in our lab work. Okay, precision, on the other hand, is how well the same measurement can be repeated or reproduced. A low or small range of uncertainty would indicate higher precision. So, for example, at the very bottom there, of A and B, A being 5.0 meters plus or minus 0.001 meters, and measurement B being 5.0 meters plus or minus 0.01 meters, which of those do you think has greater precision in its measurement? So we look at what is the range of our uncertainty as an indication of that precision. So in case A, I have 1 millimeter, tens, hundreds, thousandths, so 1,000th of a meter, plus or minus 1,000th of a meter in part A, versus the measurement in B is plus or minus 1/10 hundredth of a meter. Okay, so I have a greater variation in B, so measurement A is more precise, and you can think of that, that's 5.0 meters plus or minus 1 millimeter, so think about the meter sticks that have the tick marks all the way down to the millimeter size. That's more precise than a measurement from part B, which would be a meter stick that only goes down to a tick mark every centimeter. Okay, so that the image of accuracy versus precision that's also presented frequently is one of a dartboard or a bullseye. The closer you are to hitting the bullseye, the more accurate you are. But after, say, 5 throws of the dart, if you throw 5 darts and they're all clustered around the same spot, even if it's not the bullseye, but if they're all clustered around the same spot, that's a very precise dart throwing. So very precise measurements will cluster around the same spot, even though they may not be accurate. Ideally, we are striving for high accuracy and high precision, right? So we have all of our measurements are clustered around the same spot, which happens to the bullseye, where they are most accurate. Okay, so A we're saying is more precise, and the target analogy is a nice one for trying to remember accuracy and precision. All right, in conclusion, what do we want to be able to do? We want to be able to describe the difference between uncertainty and error. So uncertainty has to do with when we are taking measurements, what level of precision do we have, and then when we take multiple measurements throughout our experimental process, we need to be mindful of which measurements are most uncertain and which ones are going to contribute most to our experimental error, and keep track of that so that we can develop a range of uncertainty for our final prediction or indirect measurement or whatever it is we are producing. What else? We want to be able to identify the greatest sources of error, which means identifying measurements with greatest uncertainty. Provide a range of uncertainty in our lab work. Okay, so we did that, or should have done that, for our height lab. We want to be able to calculate absolute and percent error. So if we have not done that for our lab from Friday, you need to make sure you have that completed for tomorrow, so we can talk about that since we missed some people due to a class meeting at the end of class. And what else? We want to be able to describe the difference between accuracy and precision. So for the AP Physics 1 and 2 exams, we need only be able to deal with error and uncertainty qualitatively. We do not need to have to say what the propagation of error is, what differences between what standard deviations we're dealing with, or distribution of confidence levels. It would be rare, I think, even to see, I haven't seen it, a question that specifically asks you to calculate percent error. It's just a kind of normal calculation question, which aren't very frequent on the AP exams. What we do need to be able to do is talk qualitatively about it, that means to say, can you tell me where the greatest source of error is coming from and justify why you think so? So measurement tool, in particular, its level of precision or how it's being used, or as we mentioned at the end of class last time, what percentage of your measurement is that uncertainty range? So, for instance, there's a greater percentage of uncertainty from a 20-degree measurement plus or minus 2 degrees versus a 70-degree measurement plus or minus 2 degrees. The 20-degree measurement, the smaller angle measurement, has a greater percent uncertainty, since both measurements, we're saying, have the same range of uncertainty. Those are the types of things we want to be able to look at on the AP exam. On that one free response question, that's always a lab investigation, comment on the analysis of this investigation question. We always want to be able to look at that and analyze the data they present to us and say qualitatively what we can about the error and the uncertainty. That's it for this video. Be prepared to talk about our error, absolute and percent error from our height investigation from last class. That is it. Bye.